So let's take a look. Here we have two reactants and two products, and again, this only works if everything's in their gas phase. So we can say the equilibrium constant Kp is equal to the partial pressure of the two products raised to their stoichiometric coefficients divided by the partial pressures of the two reactants raised to their stoichiometric coefficients. Okay. Now, Kp, this is one of the things that I kind of struggle with. I don't know if other people do too. But I'm going to tell you right off the bat, not necessarily, in some cases it is, I think, but Kp is not numerically necessarily equal to Kc for the same chemical equilibrium. Okay. So we kind of talked the other day, on Wednesday, that Kc actually has no units, even though looking at it, you think Kc should have some crazy moles per liter units. They cancel out, nor does Kp have any units for the same reason, which is kind of nice. So I'm going to kind of show you a proof. How do Kc and Kp relate to each other for the same equilibrium? So I'll kind of take a look at that. Well, if we take the ideal gas law equation and rearrange it for N over V, N over V is moles per liter, so N over V is molarity. And then we take that concept now and basically kind of substitute it into our Kc expression. It looks like this. Okay, so our Kc then would be equal to, assuming everything's in its gas phase, the partial pressure of C divided by RT, okay, raised to the stoichiometric coefficient of C times the partial pressure of the other product, D divided by RT, raised to its stoichiometric coefficient. And then we divide it by the reactants raised to their stoichiometric coefficients, all over RT. When I was getting ready for this lecture, I'm kind of like, oh man, that's going to look pretty slick. Looks like all of our RTs are going to cancel, but hold that thought, not necessarily, because our RTs are raised to the stoichiometric coefficient, okay? They're raised to a power, so they won't necessarily all cancel out. They might all cancel out if these stoichiometric, and this is actually going to be what I get to, if basically the value of these is equal to the value of those, then RT does cancel out. So we can pull out our 1 over RT term, but make sure that we bring the exponent through like that. And then we can gather our 1 over RT terms together, and it looks like this. 1 over RT raised to the C plus D power, which is the coefficients in front of C and D, minus the A plus B power, which is the coefficients for A and B. We've kind of pulled out our partial pressures here, which is kind of what we were after. This right here is Kp, right here. So we can go ahead and substitute Kp in there, and it looks like this. So Kc is equal to Kp times 1 over RT raised to, now instead of having that C plus D minus quantity A plus B, we just went ahead and called it delta N, the change in moles. So basically, how many moles do you have on the product side minus how many moles you have on the reactant side? That's delta N. There's one more kind of switch here we're going to do. We could go ahead and simplify that, and we've arrived to a blue box that I'll have to double check. If you have, I can't remember if you have an equation sheet for your Unit 3 exam or not. I'll check. So as it turns out, Kp and Kc are related to each other this way, where Kp is equal to whatever value for the equilibrium Kc is, times R times T raised to the delta N. Now, if delta N is equal to 0, okay, anything raised to the 0th power is 1. So if your delta N is 0, then basically your Kc is equal to your Kp, which is a wonderful thing. Okay, and again, the R value that we're using is the gas equation. R, yeah, ideal gas law. Okay, so let's work a problem kind of going back and forth between Kp and Kc. So in this case, we know Kp, but we don't know Kc. So we could use that blue box equation. We're going to use that blue box equation here in a minute. But the delta N we're going to use, it's always final minus initial. So in this case, delta N is 2 moles minus 1 mole. 2 minus 1 is 1. So our delta N is 1. And the temperature we're going to have to use actually needs to be in units of Kelvin. So we need to take the 45 degrees Celsius they have here and bump it up to Kelvin. It's 318 Kelvin. Okay, so we can rearrange this to solve for, because we know Kp and want to know what Kc is. So Kc is equal to Kp divided by RT raised to the n power, which again, delta n here is 1. So substituting in, the Kp is 0.62 divided by that 0.082058 atmospheres, liters per mole Kelvin, times the temperature, 318 Kelvin. Now this is weird for me, but I do remember now when I worked these, notice that I did not, for the first time, bring any units. Units, question mark? Because in part, we said that Kc is going to be unitless. So I'm just kind of taking it at its word that it will be unitless. So if you put that in your calculator, allowing for 2 significant figures, you come up with a Kc value of 0.024. Again, unitless, given that Kp value and that equilibrium. So we'll take a quick look at these. .4. Cool. So this one, instead of Kc's, we're supposed to write Kp expressions, the equilibrium constant expression for Kp. Again, though, it's the partial pressures of everything raised to their stoichiometric coefficient. I went ahead and underlined in B, don't forget that those solids there do not appear in the expression, and C. And I just did A, I didn't do the other ones, but this is kind of like what you did in your previous homework, where they tell you how many moles of product to form, in this case NaCl, and you need to pick up nitrogen, oxygen, and chlorine, which are all diatomic elements. So I bet those stoichiometric coefficients are going to be 1/2 over there. And once you have the balanced equilibrium, go ahead and write the equilibrium constant expression. And then this last one, in this case, you are given Kc values and asked to find Kp's. They're related this way. So the delta N, for instance, then, of the first one is 2 minus 1, or 1. Then I went ahead and just kind of came up with the delta N's for all of them. Okay. Then back to one last part. All right, so this is the gran enchilada. So it kind of reminds me of manipulating equations for Hess's law a little bit when we did it for enthalpy changes. So sometimes you will know the equilibrium constant for an equilibrium that can be added to other equilibria to get an overall equilibrium of interest. Okay, so it's possible that you need to manipulate the equilibrium and then understand how the constant is affected. So we'll take a look at that right quick. So we have sulfur reacting with oxygen to form SO3, sulfur trioxide. Everything is gaseous state, but it's not. So that solid sulfur is not going to show up. So we could write the equilibrium constant expression, and it would look like this. Well, let's just say we scale that up, and we go ahead and multiply through by a factor of 2, and it looks like this. So if we multiply through by a factor of 2, that's going to change our equilibrium constant expression. So instead of the first one, it's going to look like this. It's going to be molar concentration of SO3 now raised to the second power divided by molar concentration of O2 raised to the third power. These actually, and there's going to be a rule coming up, but do you buy this that we multiplied, let's see, multiplied this by 2. Wait, how do I say this? Well, maybe that's how I say it. We call this 1 and this 2. 2 is basically 1 times 2. Okay, so can you almost kind of see that basically if you take this and square it, that's what this is. So that's kind of the way the rule works. If you multiply through by a constant, you have to take that and make it into a power. So kind of what I did was the second, for the second equilibrium, that's the Kc2 for the second equilibrium, was equal to Kc for the first equilibrium squared, raised to the second power, because I was multiplying through by 2. And that's always going to be the case. If you multiply your equilibrium by a constant, then you make that into a power and apply it to your equilibrium constant. Okay, so let's look at another little trick of the trade. This one probably works for you. What if we take that second equilibrium and what if we reverse it? And we'll call that actually the third scenario. And it's always going to be products divided by reactants. So in this case now, it's going to be O2 raised to the third power in the numerator divided by SO3 raised to the second power in the denominator. So if you look at these two, you'll see that actually they are the inverse of each other. Basically, we just flipped it. So if you swing it around the reaction arrow, then reaction equilibrium arrows, then you need to go ahead and just flip the, so that works. Another way to say that is kind of summarized here. The difference between the third equation and the second equation was that we swung it around. So then that means that the new Kc is the inverse, or 1 over the old Kc. That works. So those are a couple of tricks we're actually going to use when we work problems, and we're going to see them in action here in a minute. Okay. Oh, there's a third trick. I forgot about this. Let's just say that these are two, not elementary steps, but these are two steps that add up to be equal to the overall reaction of interest. So we've gotten some practice at combining reactions. So of course the COs will cancel, the CO2s will cancel, and this is what it looks like. Okay, so that's your equilibrium of interest down there at the bottom by adding those two together. So let's just say, and sometimes it's the case, that you know the equilibrium constant for 1 and 2. Let's say you know those, the equilibrium constant for 1 and 2, and you can kind of go back and forth between the previous slide and this slide. The equilibrium constant expression for the first one would simply be products divided by reactants, so the molar concentration of CO raised to the first power divided by the molar concentration of CO2 raised also to the first power. For that second baby step, you can see where what its equilibrium constant expression looks like. Do you see where if we were going to actually take these and if we were going to multiply them by each other, okay, notice that what would cancel would be the COs and the CO2s, okay, and we'd end up with voila. Actually, that is the equilibrium constant expression for the reaction of interest. So kind of what we've just proven is that what it says in blue italics here, if, like in this example, you can add two equilibria together to get the third equilibrium, then the equilibrium constant for that third equilibrium is equal to the product of the two. Okay? So that's a good trick, too. All right, let's see what we got now. One of the things we haven't done yet, and we're going to do a lot of it in this unit, is to kind of plug into an equilibrium constant expression. So we're going to do that in this example. This is like I think the Haber process, okay, where ammonium is formed from nitrogen and hydrogen, and it's a chemical equilibrium. And they say once the dust is settled, once equilibrium concentrations are met, one scenario is that we have ammonia equilibrium concentration is 0.016. The equilibrium concentration of N2 is 0.030. The equilibrium concentration of H2 is 0.037 moles per liter. Okay, so we're going to be referring back to those. So, for this Haber process, we can write it like this, where we have 1 mole of N2 reacts with 3 moles of H2 in equilibrium with 2 moles of NH3. We could write that expression, and we are going to write that expression. Oh, we're going to do each one of these. So notice the difference between 1 and 2 is we're swinging around the reaction arrow. We've already kind of talked about what that means. It means taking the inverse of the Kc. They have that relationship. And then last but not least, we're going to take that second equation and notice we're multiplying through by a factor of 1/2 to get another set of stoichiometric coefficients. So we're going to use those tips that we used before. So here we go. Starting with the first one. Again, these were the equilibrium concentrations that were in the original problem. So the question is, what's the value of Kc? So we need to come up with the Kc expression, equilibrium constant expression. And of course, it's been what we've been talking about. That's the equilibrium constant expression. It's the molar concentrations of the products raised to their stoichiometric coefficients divided by the molar concentrations of the reactants raised to their stoichiometric coefficients. Now, in chemistry, I get all excited sometimes. Now we're ready to substitute in. So basically, we take those equilibrium concentrations and substitute them back in, and it looks like this. So we have quantity 0.016 raised to the second power divided by, in the denominator, 0.030 times 0.037 raised to the third power. It's kind of fun, this sort of problem, because we don't have to worry about units. We're like, oh, it's Kc's unitless. So, looks like we can round to 2 significant figures. And our Kc has a value that's substantial. It means that it favors the product side. So 1.7 times 10 to the second. That's it. But now let's go ahead and look at the other two. So the second one was where we reversed it. Okay, so we think then the reverse should be 1 over that. And let's just double check. Okay, so if we reverse it, now we have a new equilibrium constant expression. Kc now is equal to, now what were reactants are products, and what were products are reactants. So we're going to go ahead and take those, plug them in again. So that's equal to 0.030 times 0.037 raised to the third power divided by 0.016 raised to the second power. Okay, rounding to 2 significant figures, we get 0.0059. Now, if you take 1 divided by 0.0059, you're going to get 170. Take 170, wait, yeah, you take a 1 divided by 170, you're going to get 0.0059, which is a check that that's the way it should be. And then the last check we're going to do is the one where we multiplied this one through by 1/2. And it looks like this. So again, we'll have a different equilibrium constant expression, and it looks like this. So your equilibrium, or your Kc is equal to, well, you can see there, now we're ready to go ahead and plug back in and see what we get. So Kc is equal to 0.030 raised to the 1/2 power times 0.037 raised to the 3/2 power divided by 0.016. So rounding to two significant figures, we get 0.077. And if you were to take the Kc we got for the second one, 0.0059, and raise it to the 1/2 power, which was what we multiplied through in order to get this third equilibrium, you do indeed get 0.077. So it's just kind of a check. It's a good check. So on to the last set of homework problems. There's 3 sets of homework problems due. And it looks like this. So it just, like I said, reminds me of Hess's law. So you have to read the problem a couple times, but I put a star next to the reaction of interest, and then I put 1 and 2 as the baby equilibria to add together. So notice that I have in purple up there that looks like we need to multiply the first reaction by -1/2. And what I mean by that is you need to swing it around the reaction arrow, equilibrium arrows, and multiply through by 1/2. Now if we do that, we're going to have to fix Kc, because Kc, it's going to be the inverse, then raised to the 1/2 power. The second one, actually, the green says just leave it alone. Take it times 1. So I guess that's my hints. I don't think I'd do it for you. But I would go ahead and do that and show that it gets you where you want it to be. That now, if you make those changes, they add up to be equal to the reaction of interest. And then when you do that, you'll have to go ahead and manipulate their Kc values. There you are. Okay, so I kind of gave you the hints in the purple and the green. And then don't forget, though, when you reverse it, the new Kc is 1 over the old Kc, and that if you multiply through by constant, like 1/2, you have to raise it to that power. So this one has 3 baby steps. The reaction of interest has a star, and it's a very similar thing. I kind of gave you hints. Looks like my hints say you need to reverse both of them and multiply by 2. Oh, and then don't do anything to the third one, I think. Okay, so very similar. And then this one, 3 baby steps. Use a similar process. So in this one, you're supposed to come up with the Kp value, but you're given Kc values. So I would come up with the Kc value and then use that relationship between Kp and Kc. For this one, let's see, determine the Kc, but you're given Kp's. So what I would do is come up with the Kp of the reaction of interest, and then go Kc from there. And last but not least, oh, okay. So this is kind of like that Haber process ammonia one that we did, that N2 plus 3H2 goes to form 2NH3. But the equilibrium concentrations are not given in moles per liter, they're given in grams. So honestly, that's one of the things you have to do right off the bat. So they tell you the mass, it's like a general chemistry 1 problem. They tell you the mass and they give you the volume, so you have to actually knock out molarity before you can work this problem. Once you get molarity, you can go ahead and tap those molarities into your equilibrium constant expression. Stoichiometric coefficients are 1 across the board. Okay, and that'll give your Kc. And then B says to, B says to go ahead and after you have your Kc, knock out Kp, and that's it. So they're all good. Oh, very good. We're not going any farther.